7 days. Not a word, not a video, not a clip.
Not a post, nothing. I wanted to test the internet. I wanted to see how bad and easy or hard you can really fool the internet. Now, was it easy? Yeah. Was it hard seeing it? Yeah. Let me tell y'all how in 7 days
I fooled the internet completely.
Yo, what's up guys? Today we're going to be doing number 52 from David Morin's Introduction to Classical Mechanics book. Yeah, let's just get into it. So the problem says, a hemispherical bowl of mass m rests on a table. The inside surface of the bowl is frictionless, while the coefficient of friction between the bottom of the bowl and the table is mu is equal to 1. A particle of mass m is released from rests at the top of the bowl and slides down into it, as shown in figure 5.38. What is the largest value of m over n for which the bowl never slides on the table? Oh, I forgot to write down m. Hint: the angle you're concerned with is not 45 degrees. Alright, so to start off this problem, let's just do a free body diagram. So this is going to be the particle m at another general position. So when it has fallen an angle theta, I'm just going to draw this out to look like a full circle, even though we're only concerned with the bottom half over here. So yeah, this would be the center, and then this normal force is a radial force, and then this is going to be the gravitational force, which acts straight down. So the angle it has gone through is going to be this right here. Okay, so after we've gotten that, let's do the free body diagram for the other one, which is going to be the big mass m, which is the mass of the bowl. Alright, so what we know over here is that we have the normal force of the ball that's rolling down, acting this way, because it is equal and opposite to this one. So let me just do this in a different color, just to show you guys. The bowl is going to be, I mean, that does not look equal in magnitude. Hold up. Yeah, just, okay. The bowl is going to be feeling this force, which is equal in magnitude and opposite in direction to the one that the ball is experiencing from the bowl. So yeah. And then also, of course, it has the gravitational force acting downward. It has a normal force from the ground acting upward. And then, finally, it has the static friction acting over here. Alright, so this static friction is actually going to be equal to the maximum static friction, Fs max, because we're asked about the largest m over m for which the bowl never slides on the table. This implies that at a larger m over m, the bowl would just slip leftward. So we want the maximum static friction because that is the friction that's going to be acting before anything slips. Alright, so what we're going to want to do first is just write out the equations for this one. Oh, and if you want to know what angle this is at, it's going to be theta over here. And just to show you that that's facts, this is going to be the angle over here. And then if you extend this out kind of, this would be the normal force on the big mass m. And then this would be the same angle right here. But let me erase that because I don't want to make it look like that's acting on the ball, because it's not. So yeah. So we have that n cosine theta. By the way, n is the normal force acting between the ball and the bowl. And then ng is the one from the ground on the bowl. So n cosine theta is going to be equal to Fs max. Alright, so once we've done that, we know that Fs max is going to be equal to mu times the normal force. But wait, which normal force? It's going to be the normal force from the table because we're concerned with the friction force between the table and the bowl and not the bowl and the ball. So this is going to be mu times normal force from the ground, which we called it. I mean, it's a table, but whatever, bro, whatever. So it's going to be n cosine theta is equal to mu times the normal force from the ground or the table or whatever the fuck. And we can just do that because it's 1. So we have that n cosine theta is equal to the normal force from the ground. Alright, so how do we go on from here? Well, we need to find the normal force from the ground. So knowing that this thing doesn't move like up or down or anything. It's just at rest in the y direction and in the x direction, but we've already got to that. We have that ng is going to be equal to n sine theta plus mg. So this is the one acting up, and then these two are acting down, so we can just set them equal to each other because the acceleration in the y direction is going to be equal to 0. Alright, so now that we have that for ng, we can just sub that back into our equation over here. Okay, and then after that, what we can do is, well, we're going to want to find this normal force and what is n. So to do that, we need to go back to the mass over here. Let me just copy this because I think it's like a good diagram that we have. Bro, please.
Please, me, I need this!
Bro, bear with me, alright? I swear it was working like 10 seconds ago. Okay, if that doesn't copy everything, I'm gonna, okay, bro. Alright, just wait. Bro, I'm literally gonna crash out, bro. Bro, why isn't, okay. Anyways, we want the equation of motion for this ball so that we can determine the normal force. So, if this is going to be, this is just going to be our positive radial direction, which is going to be towards the center of the circle. I know usually the convention is the other way, but we're going to do it like this, because as long as you stay consistent, you can like literally do whatever the fuck you want. So, this is going to be n, because n points all the way in the r direction, and then we need the component of gravity that points in that direction. So let's draw this out again. We know that this is going to be equal to theta. So if we just have a line like this, this is also going to be equal to theta. So it looks like it's going to be the sine component. And since it's acting in the opposite direction as a normal force, we're just going to do minus. So it's going to be minus mg sine theta. And if you're wondering how I got this angle, this is theta, this is 90 minus theta, and then this is theta again, because there's a line over here that I've superimposed. And then this is going to be equal to m times the centripetal acceleration, which is, in a second. We're going to get to that. AC is equal to v squared over r. And then r is just going to be the radius of this ball, which I think we were given. Low-key, I don't think we were, but then that means it's going to just cancel out. Trust. I've done this before. Okay, so n is equal to m g sine theta plus v squared over r. I don't know how much factoring that out is going to help us. Probably not, but whatever. So now that we have that, we can just plug this back into the equation that we have right here. So we have mg sine theta plus mv squared over r times cosine theta is equal to the same thing. Oh my days. Sine theta plus mg. Okay, word. Alright, so now what we're gonna want to do is, let's just pull this over to the side over here. Hopefully you guys understand what I'm doing over here. And like, if you don't, or if you're like confused about like literally anything, like just go in the comments, because I will be responding to those. Okay, so now that we have that, you may be wondering, well, alright, like low-key, like what is v squared over r? We will find that out in a second, but first let's just get the thing set up. I do believe we want the maximum of m over n. So let's just do this. Factor out the m. It's equal to mg, okay, and then now what we're gonna want to do g over, hopefully I don't fuck this up, but that would be embarrassing. I'm like also low-key looking at my like previous solution just to make sure I don't make any like stupid mathematical errors, because I did this problem before. But yeah, so then that's what you're gonna want to get for m over m. Okay, so now we have to tackle what's v squared over r. So pretty easy way we can do this, and I was gonna use this thing again, but like, bro, it's like not working with me. So let's just use it, but we're gonna have to erase a bunch of shit. Alright, so we're gonna want to do conservation of energy. So work of non-conservative forces is equal to the change in energy. And since we don't have any non-conservative forces when we're looking at the energy for this ball, don't have any of those forces acting, so we can use conservation of energy. So I just wanted to have this over here so that I can give you guys a visual. We know that this goes to k0 plus u0 equals k plus u. The initial energy equals the final energy. So the initial, we're going to count this as the initial, and then like this position over here when it first got released, and then for the final it's just going to be when it has fallen like by an angle theta. So k0 at the beginning is going to be 0 because as you may remember, it was released from rest. And then u0, we can just choose this to be where we count 0 potential energy. So at the top over here, this is going to be r. The height is going to be r. And over here, I'm going to draw it a bit higher just so we can tell. And this over here, this is going to be h. I'm just going to call this h. And then this over here, let me draw that so that's a little bit more obvious. This is r, and if we want this thing over here, this vertical line, that's going to be d sine theta. So h is going to be equal to r minus d sine theta. And yeah, d is r, my bad. So it's going to be r minus r sine theta. Because, yeah, this over here is the hypotenuse. I've just been doing a lot of like rolling angular momentum problems, and like I always called it d. So, but yeah, that's gonna be r because it's. Let me just draw it out here just so it's extra clear because I'm like kind of waffling right here. But this is theta. This is r. This is what we want. So sine theta is going to be this question mark over r. So r sine theta is going to be the length of that question mark thing. Alright, and then let's move over here because we got the visual out of the way. So we have, just separate this off, we have that u0 is equal to k plus u. So u0, as we said, well, this is going to be mg. The height initially is going to be r, is equal to 1/2 mv squared. It's just the velocity when it has gone through that angle theta, plus, and then we just got this out, this h, r minus r sine theta, the final h, which is the one at this position. The initial one was, remember, when it was up here. Okay, bro, this is a lot of like steps, which is why it's a 3-star problem, but yeah, let's just expand this out. So we can cancel this, and then bring this to the other side. And cancel out the m, and we have 2gr sine theta is equal to v squared. So 2g sine theta is equal to v squared over r. Why did I solve for v squared over r? Well, because we have v squared over r. When you go back to our m over m, we have this over here, so it's just easier to do that. So then what we can do is plug in for what we get for v squared over r. As we just found, it's Okay, so g sine theta plus 2g sine theta, and then cosine theta minus sine theta is going to be the m over m. Alright, fine, and then let's simplify this out a little bit. This is going to be 3g sine theta, and then this is going to be cosine theta minus sine theta, and then these g's, whatever, they cancel. 3, oh my god, bro. It's almost over, guys. It's almost over. Alright. Okay, bro, now that you have that, now you just want the derivative, because this is the expression for m over m, right? Oh, that kind of looks ambiguous. Okay, the m over m. So we want the maximum m over m. So to get the maximum m over m, we need to take the derivative of this expression with respect to theta, because I do believe, what was the question asking again? Yeah, what is the largest value of m over m for which the bowl never slides on the table? So we want the maximum, we're going to take the derivative with respect to theta, and then we're going to get a theta, and whatever theta we get, we plug back in to the m over m, and then that is going to give us the maximum m over m. Okay, so let's rewrite this as 3 sine theta cosine theta minus sine theta, and then to the power of -1. Now we can use the chain rule. -2, and then the derivative of the inside function, which is going to be pretty long, but okay, so it's going to be a product rule. So first differentiate this and then leave the parentheses alone. And then differentiate, or no, leave the first term alone, and then differentiate the parentheses. So the derivative of cosine is negative sine. Derivative of sine is cosine, because this negative sign is going to be negative cosine. Okay, so then we have that, and I believe that should be it, hopefully. Okay, so this right here is what we're concerned with, because this is the numerator. Oh wait, let me make this extra clear. That's gonna be this. And then we're gonna need to set that equal to 0. So basically what we just did is we took the derivative of this expression right here, and we set it equal to 0. That's just a classic maximization, minimization, optimization, whatever the fuck you want to call it. In this case, maximization. So since this is in the denominator, like, we're like low-key not concerned with it, and then like this is also just like a -1, just like a constant, we're not concerned with it. It's not gonna be useful for determining what theta is equal to 0, because it's just gonna get multiplied by 0. And then like we're also assuming that we don't get a theta that's gonna make this infinite, if you get what I'm saying. Bro. Did that stop recording me? Okay, no it didn't. This has been 20 minutes, holy shit. Oh my god. Bear with me. I don't know if I'm just being slow, or if this problem is just extremely long. Okay. Yeah, okay, so the numerator set it equal to 0. Okay, by the way, if you're still confused about like the denominator thing, like we could have theoretically, we just could have like had this here, and then 3 sine theta. I'm just gonna write this really quickly. Could have had this here, but then we would have cross multiplied with 0, and then it would have just given us the numerator. Now we can just expand this out. Remember when I said we're almost done? We're like actually not almost done. We still need to do the whole thing with plugging back in. That's gonna be -3 sine squared theta. And then I need to tell you guys about some trig identities in case you didn't know that they existed. Which is totally okay, because I don't keep track of them that much either. Okay, so we have everything multiplied by 3. Let's just get rid of that. So we have cosine squared theta minus sine squared theta, and then -2 sine theta cosine theta is equal to 0. Okay, so you guys may know that this is equal to sine of 2 theta, this part. But did you know that cosine of 2 theta is equal to this? Namely, cosine squared theta minus sine squared theta. Okay, and let's make this extra clear too. Okay, I knew about this one, but like this one, like, not really. Like, you barely use that one. I mean, I don't know. I barely use that one. Okay, so cosine, we can just rewrite this in terms of shit that I wrote up there. Minus sine 2 theta is equal to 0. Okay, fire. So now we have that cosine 2 theta is equal to sine of 2 theta. Okay, so now we have that 1, if we divide both sides by cosine 2 theta, we have that 1 is equal to sine 2 theta over cosine 2 theta. Okay, so then they're going to have that 1 is equal to the tangent of 2 theta. Okay, now you can do this whole like tan, arctan, whatever the fuck shit, or you could just be like, tangent of what is equal to 1? Tangent of 45 degrees is equal to 1. So tangent of 2 times 45 over 2 . And then this is gonna cancel, so just to show you that tangent of that is equal to 1. But what I was saying here is that 2 times 45 over 2, so your angle theta is going to be equal to 45 over 2, which is equal to 22.5. Yeah, because like I said, if you cancel all the 2's, then you get a true thing, the tan 45 is equal to 1. But if you want to do this a bit more like formally or whatever, then you can do, because like sometimes it does get more complicated and you can't just like do that. Oh, whoops, arctan 1. Arctan, my bad. I'm tweaking out because this problem is taking forever. Okay, so arctan of 1, like we said, 45 degrees is equal to arctan, tan, those cancel out, 2 theta, 45, oh my, why is my pen tripping, is equal to theta is equal to 22.5. Okay, banger. Okay, so now that we finally have that, now we can plug that back into the amogram equation. Okay, so now this is going to be the amogram max is equal to okay, and then when you get that, you get 1.61. Okay, and like just trust me that you get 1.61, like you literally do. Okay, like I'm not gonna put that in a calculator right now, but I did put it on Desmos when I did the problem, so like I know that that's gonna be what it's come out to. Just trust me, bro. All right. Okay, so now that we have that, we have the problem. That's the answer to the problem. Jesus Christ, bro. That took a lot of work. But yeah, again, as always, if you have any questions, please just let me know in the comments, because I kind of was waffling for some of these parts, so if you would like to know anything that, like, confused you, just let me know and I will give you an answer as soon as I can. But I have, like, a shit ton of final exams, so So you might have to wait a little bit on that, but then in the winter break, I'll be uploading more. Going with some more electromagnetism content because we're going to be doing electromagnetism during the winter break. Yep. All right. See you guys. Albert, Kiss and I Hope, they caught us, whether they like or not. I want to show you off. I want to show you off. I want to brag about it.